Ladies and gentlemen, we're about to begin phase 2 of our evil project. Or is it phase? I don't know phases.
Anyway, so we are going to look at one more example of a partial series dealing with an arithmetic series. So if we have the series 15 plus 8 plus 1 plus negative 6, you should see what's happening. You should kind of clearly see that it is, in fact, an arithmetic series. The problem says find the sum of the first 12 terms in the series. Okay? So 12 is not such a big number. We could just find the first 12 terms and just add them up. There's a faster way. There's a formula, right? So what we want to do is, well, first of all, to refresh your memory about the notation, another way to write this is capital S sub 12, okay? Or also meaning the same thing using sigma notation, okay, where we have a k equals 1, indicating that we want to start with the first term and end with the 12th term, and you want to add up all the terms in between the first and the 12th term, inclusive, to have our answer, to have our partial sum. So what we need to put here is the formula, and using a k instead of what we're used to, being an n, okay? So we have what? The common difference is negative 7. The formula of this corresponding sequence would have been, what, 15 minus 7 times n minus 1, which would become negative 7n plus 22. So what we have here is negative 7k plus 22. This is another way of writing this. This is a much more compact way of doing it, but this also means the same thing. This capital Greek sigma means sum, right? The formula for this, to actually do this math, to evaluate it, is n, which in this case is 12. You want to find the partial sum of the first 12 terms. So we have 12 times t sub 1, which is 15 in this case, plus t sub n. Now, n in this case is 12, so we've got to find that 12th term, whatever that is, and then divide by 2. 12th term is not so bad to find. Let's just use the formula we have here. Okay, that's why it's kind of important to get the formula, first of all, so you can easily find that last term. You need that last term. You got to have your first term, just like with sequences, but now you've also got to get that last term, okay, the value of the last term in your partial sum. So let's plug in 12 here. Negative 7 times 12 is negative 84. Negative 84 plus 22 is negative 62, okay? So this is going to be replaced with the negative 62. And now we can evaluate the partial sum. 15 minus 62 is negative 47. So we have now 12 times negative 47 divided by 2. Let's just kind of do this quickly by hand. That becomes 6 over 1. 6 times 47. Well, let's do 5 times 47, all right? 10 times 47 is 470. So 5 times 47 is 235. 235. We need one more 47. So 235 plus 47 is 284. So we have negative 284 as the partial sum, okay? This is just another example of an arithmetic partial sum, and we're going to get into more with sigma notation, but I just wanted to review this. This is really the key. The formula is really all you need to know to do this, okay? It just involves the first term, value of the first term, value of the last term in your partial sum, plugging in the number of terms total, and then dividing by 2, okay? That's that. Let me erase this and give you a geometric example. All right, now let's improv a geometric series. Let's still deal with starting with the number 3, say. So let's go 3, 6, then 12, then 24, and so on and so forth. Clearly, it's a geometric series because we're starting with 3, and then we're multiplying by the same number each time, that number being 2, right? There's really, it's a pretty complicated derivation of the formula for a geometric partial sum, so I'm just going to tell it to you. Okay, for a geometric partial sum, capital S sub n, we have I have to look at this because it's a little bit tricky where the subscripts go. It's not one of those formulas you easily have access to in your head, all right, because the derivation is a little more complicated. But it is, again, dealing with t sub 1 times 1 minus r to the nth power. Now, r is that ratio, the common ratio. In this case, it's 2, all over 1 minus r. And where this comes from is in the textbook, but it's pretty complicated. You're not going to be held accountable to really understanding where that comes from. It's a lot of manipulation algebraically. The arithmetic one is much more friendly to understand. Okay, this is the formula for a geometric partial sum. All right. So say we wanted to find the sum of the first. Let's do 10 terms. Okay. Let's say find s sub 10 for this stuff. All right. Now, in other words, that could have been written like this, right? Sigma k equals 1 to 10. But in this case, we've got a geometric sequence, essentially, geometric series. All right? T sub 1 is 3 times the ratio is 2 to the k minus 1 power. That is what our sigma notation would look like in this case. Okay? Same idea as with an arithmetic. You just write the actual formula to the right of the sigma. That's the notation. This means finding the sum of the first 10 terms in the series. Now, we've got to apply this formula. T sub 1 is 3 times 1 minus r is 2, right? The ratio is 2 to the nth power, that is 10 in this case. Okay? It's going to be a pretty big number, right? These numbers are going to jump up pretty fast. If we're adding them all up, it's going to be pretty big. Divided by 1 minus r. So just 1 minus 2. Okay? You see this is going to be negative 1. This is going to be a negative number also. So it'll kind of cancel each other out to make a positive. Let's see if we can do this by hand. I don't know if we can, but we have 3 times. I know that 2 to the 10th is 1,024. So we have 1 minus 1024. We have negative 1023 over negative 1. All right, so it's going to be a little bit tricky, but we're dividing 3 times this by negative 1. So a negative over a negative is going to be positive. All we really have to do is 3 times 1,023. Not so bad. 3,069. Okay? So that is how to find a partial sum for a geometric series. All right, so now you have a formula for a geometric series partial sum and a formula for an arithmetic partial sum, okay, and which you'll always be provided with on quizzes. And also you have some exposure to the sigma notation. All right, hope you'll have a great holiday with your families. See you all in 2014. It's a lot of kind of crazy. I remember when it was 1983. Well, no, I don't. I was born that year. But anyway, you get the drift. Have a great time, great holiday, be safe, enjoy it. Awkward silence segue, sorry.